Algebra 2, Chapter 11, Section 3, Applications of Logarithms to Modeling. The balance of a bank account begins at $32,000 and earns 3.5% interest per year. When does it reach $70,000? So we can set this up using an exponential equation. We know the value of the bank account will be equal to the initial balance, $32,000, times the annual growth factor at a rate of 3.5%. That'll be 1.035 to the t power, where t is time in years. We want to know when does that value reach 70,000. Okay, so we can solve this equation using logarithms. We divide both sides by 32,000. We have 70 over 32 is 1.035 to the t power. Now if we take the logarithm of both sides, we will have the log of 70 over 32 equals t times the log of 1.035. Dividing both sides by log of 1.035 will give us t. Using a calculator, we can find an approximation of the answer. Log of 70 over 32 is around 0.34 divided by the log of 1.035 gives us 22.75 or so years. 22.75 years to reach $70,000. Between the years 1991 and 2001, the population of Naples, Italy decreased on average by 0.605% per year. In 2001, the population was 1,004,500. If the population continues to shrink by the 0.605% per year, what will the population be in 2010? So if we set up an equation, in 2001, we have 1,004,500 times the 1.00605. Oh, no, that's growth. This is decay, right? So for decay, b is 1 plus r. We have to subtract, or we have a negative rate. So if 1 minus 0.00605, we might even need a calculator to do that. 1 minus 0.00605 is 0.99395. 0.99395. That's our b, our growth factor, because we're shrinking here. It's decay. To the t. Really, we could do t minus 2001 because we start at the year 2001. So we can plug the year in for t, and that'll give us the value, the number of people in Naples, assuming this decay rate. So when does this equal, or what will this be in 2010? We need to subtract, and this is very similar to the problems we've done before. So 2010 minus 2001 is 9. Our growth factor, 0.99395 to the 9th power, gives us 0.946, the factor for 9 years. Multiplying that by our starting population of 1,004,500 gives us a population of 951,110 people. 951,110 people. For part A. Part B, when will the population reach half of its 2001 level? In other words, when will it equal 1,004,500 divided by 2? Well, if you notice this equation that we need to solve here, the 1,004,500 appears on both sides. If we divide by that value, we'll cancel those to 1. So we'll have just this equation, 0.99395 to the t minus 2001 equals 1/2. And if we take the log of both sides, we can find t minus 2001 is log of 1/2 over log of 0.99395. And if we use a calculator, log of 1/2 divided by the log of 0.99395 will give us 114.2 . So we'll have t minus 2001 is 114.22. And then adding 2001 to 114.22, we get the year 2115.22. So, about 1/5 of the way in to that year is the year that we'll reach that population level. The population of Nicholasville, Kentucky in 2010 was 28,015, while the population of Lexington, Kentucky in 2010 was 295,803. Assuming the average annual growth rate for Nicholasville is a constant 42% and Lexington's is 12%, when will the population of Nicholasville be the same as Lexington? So we need to set up a growth formula for both of these. So we have 28,000 for Nicholasville, 15 people. We're assuming that it grows at 42%, so 1.42 to the t minus 2010. We want to know when are these equal, right? Because we're trying to find out when the populations are equal. So that the growth of Lexington is modeled by 295,803, and the growth factor here is 1.12 for the 12% growth rate to the t minus 2010. Okay, so we could take the logarithm of both sides now, but it's going to result in a mess because we'll have a lot of logarithm work to do. First, let's simplify this to get one factor and one number in front, or one number on one side. So we need all the t things on one side and the other things on the other. So if we divide by 28,015 on both sides and divide by 1.12 t to the minus 2010 on both sides, that'll give us an equation where we have 1.42 t minus 2010 over 1.12 t minus 2010 with the same exponent. So we could write 1.42 over 1.12 all to the t minus 2010 since the exponents were the same. And then here on the right hand side we still have the 295,803 divided by the 28,015, which kind of get the ratio of the initial populations. And that gives us a much simpler thing because now we can take the log of this, pull the t minus 2010 in front, and log of that. So we'd have t minus 2010 is the log of 295,803 over 28,015, all divided by the log of 1.42 over 1.12. Getting our calculator back out, we can then find this value. The log of 295,803 divided by 28,015 is 1.0236. Divide that by the log of 1.42 over 1.12, and that gives us 9.93. So we'll check this and make sure it's right, because this seems kind of strange. 9.93 years from 2010, or basically now, year 2020, is when they would be equal, which doesn't seem to make much sense. So let's plug in 9.931. 1.42 to the 9.931 times 28,015 gives us 911,000 people. I think these growth rates just make no sense is the problem. 295,803, and I think I actually know why, because I understand now. Okay, 295,803 to the times 1.12 to the 0.9931 power. Also, to the 9.931, 9.931, 1.12 to that power times 295,803 gives us the same number. So we got the right answer, but the problem was set up wrong. This is not annual. This is what threw us off. This is not annual growth rate. This is the decannual, I think is how you say this. Sorry, not decannual. It's called, that's the wrong word. That's a made-up word. Decennial. Decennial growth rate. So that means every 10 years. So that this t is in tens of years since 2010. Let's just erase the minus 2010 part and kind of fix our work here. So t is just in decades, basically. Okay. So 9.931 decades. That makes more sense. Okay, so in 9.931 decades, that would be 99.31 years. So 9.931 decades would be 99.31 years. That's the win. Okay, that's the answer to the first question. The next one is what then would the population be? So we already found that out here as almost a million because we already plugged this in. So we have 911,000 because all we have to do is plug in 9.931 as the number of decades to one of these two expressions to get the answer. So both of these came out to about 911,500. And this one was 19, this one was 563. We'll just use the second one. So both those answers are close enough to be right because we rounded the 9931 a little bit to get that answer. So 911,563 people. And the last thing is more subjective. What do we think? Is this realistic? And I think the answer to is this realistic is no. And I think the reason it's not realistic is the growth rates will not remain constant. And you can see this in history. The growth rates never remain constant. The growth rates will not remain constant. It's not likely that Nicholasville will ever be as big as Lexington for various reasons. Now, just because Nicholasville grew a lot in one decade, we can't project that forward forever, this growth rate over Lexington's growth rate over a decade. Let's go on to another example. The size of a population of frogs is given by this expression. What is the initial size? Of course, that would be 185 frogs, the part not with the power of t. B, how long does it take for the population to double? Again, the initial size doesn't really matter. We can write 185, 1.135. So the t is double 185. And then when we can divide both sides by 185, and we just get this equation. 1.135 to the t is 2. An exponential equation we can solve with logarithms. Taking log of both sides, we get t log 1.135 is log 2. Because we can pull the t in front, we get log of this 1.135 to the t. Using the properties of logarithms, we can pull the t out in front. Dividing both sides by log of 1.135 will give us the answer for t. Using the calculator, we can get an approximate answer of log 2 over log 1.135, 5.474. 5.474 would be t. So it takes about 5.474 years. C. How long does this population take to quadruple? Well, if it takes 5.474 years to double, it will take double that to quadruple. So we can just multiply that by 2. 5.474 times 2 is 10.948. $10.948 years. And for octupling, we would need to double again, because double, quadruple, double 4 is 8. So to double another again, we need another 5.474 years. Just add another 5.474 to get 16.422 years. Polonium-18 decays at a rate of 16.578% per day. What is the half-life of polonium-18? So to find the half-life from the decay rate, think about the factor part of the exponential decay. So first, let's find b. So b is 1 plus r. R here is negative 16.578%, so negative 0.16578. So b will become 1 minus 0.16578, 0.83422, 0.83422 is b. So to find the half-life now, we know 0.83422 to the days, if t is in days, times some initial value would be the current quantity. And so it'll have half of that quantity when it equals that initial quantity times 1/2. So if this were a, when it's 1/2 a, and the a's cancel like we saw in the examples. So to find the half-life, all we need to do is find t log 0.83422 equals log of 1/2, which we can write as log of 1/2, skipping a bunch of steps. Log of 1/2 over log of 0.83422. Because when I take log of both sides, t comes in front, and I can divide both sides by log 0.83422 to get log of 1/2 over log of 0.83422. So we can find the half-life then, log of 1/2 divided by log of 0.83422 gives us 3.824 as t of half-life. 3.824 days is our half-life. And the second part, does the mass of the sample change the half-life? No. The mass doesn't matter. The mass of the sample cancels out. So just going back over those examples we've just done, we see to find doubling time, we just have to solve this exponential equation. The growth factor to the t power equals 2. For half-life, we just had to solve b to the t is 1/2. So in general, to find when the growth is a factor of any sort of generic factor f, we just have to solve the exponential equation b to the t is f. Taking the log of both sides and taking t in front, because remember log of b to the t is this equivalent to t log b. So t log b is log f, dividing by log b, we get t is log f over log b. So you can just memorize this technique for finding half-lives and doubling times. Whatever your factor is, you put up here in the numerator. So if you want to find a doubling time, it's log 2 over log b, where b is the growth factor. And if you wanted to find a half-life, it's log of 1/2 over log b, where b is, again, the growth factor, although b will be less than 1 if the half-life is positive to be decay.